Good afternoon, everybody. Welcome to Fall Afternoon on Chem 170 Organic Chemistry with your host, me, Dr. White. Hi. All right after lab today, I will be sending out, I'll wait until Joe logs in. All right, I think he's logged in. Right after the lab today, I will send out an email with the password for. All right, Megan, that's fine. A lot of people have been having trouble with internet. Let's give Megan a minute or a little second or two to log back in. She disappeared. Well, I'll get going and I'll repeat it when she gets back. All right, after lab today, I will send out an email for test. Oh, wait, there she is. Are you back? Is it a little better, Megan? I don't know. But anyways, right after class today, actually lab, I'll send out an email for test number 3. It's like test 1 and 2. Hopefully you've downloaded test number 3 from D2L. If not, you have plenty of time. And with the password, you can open up that PDF file and take test number 3. You'll have until 11 a.m. tomorrow to upload test number 3 answers as a single PDF file. You've done it before, keep on doing it the same way. And that will be test number 3. Now, I guarantee by Sunday, 1 p.m., if not sooner, that I will have, I forgot to pin myself. Ouch, I pinned myself. That was a bad joke. But anyways, that's keeping my screen on front for everybody. After, I guarantee by Sunday, 1 p.m., not sooner, probably a lot sooner, that I will post your scores for test number 3 in D2L. Also by Sunday, 1 p.m., if not earlier, I will email you individually your individual answer points for each answer on test number 3. I'm thinking of 4, it's 3. Semester's not that gone yet, getting there. All right, there's a lot on my mind. And what's on my mind is, let me remind you, next Monday, I'm going cataract surgery for this eye. 2 weeks later, I'll get the other eye. So I won't be here for lecture. What are you going to do? By Sunday, I will post in YouTube a full lecture. Like if I'd been there, you're just not there. And what I'll probably do is take an earlier lecture, edit it and post it. And I'll send out an email reminding you I will be here on Wednesday. On Wednesday, I will go through a week from today, all the answers for test number 3. Normally I would have done it Monday, but since I always cut it out of the video, I'm not going to do it. All right, so that's the game plan for today. We'll have, I want to go over some stuff, and then we'll have our lab. Then I'll send out the email. Any questions? All right. Well, in that case, let's see. All right. A lot of people have been having trouble with internet. What was it? Yesterday in DuPage County, which affected the other school I teach at College DuPage, Comcast had a big outage, and the school itself was down, internet and everything, and a lot of my students were also affected. I wasn't, luckily. All right, let's get going. All right, what I'd like to do today is, because I sort of, I don't know, rushed through it, but went through it, is go through a few more things from fats and oils that I think are important for you to know for test 4, not today's test. And then we'll go into a new chapter. I better warn you, that new chapter is really dangerous. You can put on a lot of weight from that new chapter. It's carbohydrates. All right, I thought I opened it. Hang in there 1 second. I didn't. I've got to cut up a better phrase instead of saying hang in there. Please wait. If you have a good idea, email me with it. All right, let's get to the whiteboard. All right, the first thing I like to remind you is that a triglyceride of fat or oil a fat is a triglyceride that's a solid or semi-solid at room temperature. Oil is a triglyceride that's a liquid at room temperature. Oh, one thing I should say, if anybody has any questions about test three or anything else, always feel free to ask. Because in my class, as you know, and in my world, there's no such thing as a dumb question. Now, the basic structure for all fats and oils is this triglyceride, which is really a 3 esters, triester. And the only difference is between the different fats and oils is what's our prime and our double prime. Now, as I reminded you, each one of these is an ester. And all the chemistry you've learned about esters, hopefully you'll know later on today, is valid. And therefore, if I take a triglyceride and react it with acid, and water, and we'll write for triglycerides the ester backwards, acid and water, you get the alcohol plus the carboxylic acid you would have used to make that ester. And in this case, ester 1, 2, 3. Well, ester 1, you'll get this alcohol plus this carboxylic acid. Ester 2, you'll get this alcohol plus this carboxylic acid. And ester number 3, you'll get this alcohol, and together that's called glycerin. And you'll get this final carboxylic acid. That's a bad looking C, that's better. And it's totally bad looking. On a whiteboard in a classroom, I can do the same thing. Now, These carboxylic acids come from fats, and those type of carboxylic acids are named fatty acids. And I asked you to learn two different fatty acids, a monosaturated, or I should say, a saturated fatty acid that I asked you to learn is stearic acid. And now I'm going to be using parens. That means CH2 is repeated 16 times. And you should know how to draw the structure of stearic acid. And the other, which is a mono unsaturated, mono one unsaturated double bond, Mother Nature never did triple bonds, is oleic acid. And there, you have one double bond that can be cis or trans. And notice 7 plus 7 plus 2, 16, 17, 18. This has 18 carbons, and this has 18 carbons. And a way to show fats and oils from certain products, and those products you should know. Tallow is beef fat. Yellow grease and white grease are two types of pig's fat. And both of these are very important chemicals, yes, chemicals, or as we say in the chemical industry, feedstocks or starting materials to make a lot of things. Example, all your bar soap mostly is made from tallow and some pig's fat. There's more tallow available than pig's fat, but the yellow grease, white grease is cheaper than tallow by 1 to 3 cents a pound. If you're buying 100 million pounds, that makes a nice difference, savings. Now, because of that, if I were to ask the following, H plus or HCl, remember this is H plus. What are the products of that? Well, what do you do? Well, for tallow, white grease, and yellow grease, I asked you to use the following representation. Where this is R sub S, O, and S. What do I mean by that? If we go back up, this part I'm calling R sub S. This part I'm calling R sub O. So a quick way, and don't do this on a test if I ever ask you to draw the structure, but for stearic acid, you can abbreviate it this way. For oleic acid, you can abbreviate it this way. And those are the two fatty acids, a quick way. And that shows you down here. Hold on, I think some people are writing. Everybody done copying this down? Give me a thumbs up. Okay. I think everybody's done. Remember, I've got the fastest mouse wheel finger this side and the other side of the Mississippi River. In other words, throughout the whole United States, probably. All right, so the question would be, now when you see either tallow or white grease or yellow grease with HCl and water, what do you get? Well, these are three esters, and the general equation remember, this is H plus hydrochloric acid. H plus is tells you any acid, and you get back the alcohol plus the carboxylic acid you would have used to make that ester. And with that, I'm going to let you have some fun. What three products do you get? And what I mean by that are different products. I'm not asking you to balance the equation when you do this reaction. Your turn. One of these years, I'll get game show music to play. You don't want to hear me hum any. It'll ruin your day. It'll ruin your week. It'll ruin your month. Ruin mine too. Dr. White never had an inkling of being a singer. Even when I sing to songs, I put on headphones. All right, I think everybody's done. Let's take a look at this. We have three esters. 1, 2, 3. Here's the general reaction for acid hydrolysis of an ester. And the first ester, you'll get this alcohol plus, notice, stearic acid. Second ester, you'll get this alcohol plus oleic acid. And the final ester, you'll get this alcohol, so you actually get glycerin. And you'll get another stearic acid. Well, I don't have to put it down because I just asked what products, not how many. Now, if you want to write it down again here, you can, or if you want to put a 2 in front, you can. You don't have to, but these are three products: glycerin, stearic acid, and oleic acid. And that's really the main things your body produces when you eat anything with made from beef, has beef fat in it or pig's fat in it. So if you had bacon or hamburgers or hot dogs or whatever, this was going on in your stomach. Now, because of that, something I didn't mention earlier, and this is sort of new stuff, you should know how to describe with words in a general reaction what happens in your stomach when you eat a fat or oil, or something with a fat or oil. And what's the key functional group in a fat or oil? An ester. So if you chew your food, like my mother taught me when I was younger, she said, if you don't chew your food, you'll choke. Chew it before you swallow it, or you'll choke. I found out she wasn't lying to me because one time I choked. But anyways, when you swallow it, it goes into your stomach, and what happens? There's acid and there's water, so that's acid hydrolysis. of an ester. And you should know how to describe it with words. What happens when you eat a fat or oil? Now, the general reaction is an ester, and you can write it this way or the other way. Either way doesn't matter to me. Acid, you can either put H plus or HCl. And water. And what you get back is the alcohol plus the carboxylic acid you would have used to make that ester. And you should know this. Now, in this chapter, an important concept I talked about was like dissolves like. And that means polar things are soluble in polar solvents. And nonpolar substances are soluble in nonpolar solvents. If you mix the two together, polar and nonpolar, they won't dissolve. They're not they don't form homogeneous solutions. And when you get that down, let me know. Thank you, Joe. All right, everybody done? Let's move on. And the question is, what's polar or nonpolar? And you should know water is the most polar substance. Alcohols are polar. Another type of alcohol, which I'll teach you this coming chapter, sugars. Like sugar, like you use in your coffee or tea or cooking, and salts, which we won't cover in this class because it's organic. Now, nonpolar substances you should know are vegetable oil, gasoline. I'll use the trade name Vaseline, which is also known as petroleum jelly, baby oil, which is why people use it because it keeps water, moisture off a baby's private parts. And finally, the most important for this class, dirt and grease. And that's a list of polar, nonpolar things you should know. I hope you're finding this review useful. And when you're done writing it down, give me a thumbs up. So that's the disadvantage of being on Zoom in a classroom. I'll have to look around and see people are giving me a look. Get to work, Dr. White. All right, what does this lead us to? How soap works. There are a couple of things I would like you to know leaving my class. One is how to describe with words and a general equation what happens when you eat something with fat or oil in it. And the other is how does soap work? and you should know how to describe this. Say somebody comes up to the street and taps you on the shoulder. Do you know how soap works? And you can tell them. You should know the structure of soap in general. Soap has a long nonpolar tail, like in stearic acid or oleic acid, and it has a polar head, like in the carboxylate anion of stearic and oleic acid. And the carboxylate anion, sodium stearate, sodium oleate mixture, as I showed you, what was it? One day I think I had my show and tell in a bar soap. That's really all there is, plus a few other minor things. Now, if you look at your hand and you happen to have a microscope or a magnifying glass, a real heavy, big one, and you see a little piece of dirt, water looks at dirt and says, I'm polar, you're nonpolar, forget it. We're not going anywhere together. But when you use soap, the nonpolar tail of soap is attracted to the dirt, and the polar head wants to stay all around, far away from the dirt. And I'm just drawing a few, but it totally surrounds the dirt with molecules of soap. And you should know when dirt is surrounded by soap, we call that a micelle. And now water looks at the micelle and says, I'm polar, you're polar, because it only sees the outer polar heads, and says, you're polar, I'm polar, let's go down to drain together. And it comes off your hands or anything else you're cleaning with soap, your clothes, your dishes, your car, whatever. And lo and behold, you're clean. And you should know that. Again, and one thing I forgot to bad Dr. White, the most important thing to remember about how soap works is this is the whole key to the puzzle. And I should have put this down earlier, at least I didn't forget to. Again, how does soap work? Soap works. Soap, you should know the general structure, nonpolar tail, polar head. Because of light dissolves light, dirt is nonpolar, and therefore water will not interact with it. But when you use soap, because of light dissolves light, the nonpolar tail is attracted to the dirt, the polar head stays as far away as possible, therefore surrounds the dirt, the outside, with this whole thing is called a micelle. You should know that. And water looks at the micelle and says, now sees the polar heads, because of light dissolves light. I'm polar, you're polar, let's go down to drain together. And the last thing I would like to talk about in this mini review, remember, saponifiable lipids are the fats and oils. Non-saponifiable lipids are steroids, and those are your hormones. And you should know how to draw the steroid ring skeleton. Oops, I should know too. My head was not where it should have been. Let's try this again. Sorry about that. And the ring skeleton Hold on, I got to change the angle of my writing pad. Let's do this again. Two 6-membered rings fused together at this carbon here, 12 o'clock on the second ring. I'm having a bad ring drawing day. Sorry. I have had bad hair days. That's better. Another 6-membered ring. And right to the right of the third ring, you have a 5-member ring. So you have A, B, C, and D, 4 rings, and you should know that. And that's a quick review of stuff you should know from fats and oils, plus the other stuff. Oh, that reminds me, next Wednesday, I will go through the fats and oils problem set. I'd like to do that live in case you have any questions. All right, any questions on that so far? I thought that was a good thing that will help you out. And with that, it's time for a new chapter. And what's that new chapter? It's real dangerous because it can be very fattening and unhealthy if you're not careful. And that new chapter is carbohydrates. Now, quick little thing, you don't have to write any of this down. It won't be on a test. We're going to talk about this in the next chapter, biochemistry. Now, for some reason, well, first of all, biochemistry is the study of chemical substances that are found in things that are alive and how those chemicals interact with other substances. And it's a whole area of chemistry that's quite important. And I'm not a biochemist, but I'm an organic chemist. And most of the chemicals that are found in biochemistry are organic molecules. And what I want to mention is functional group chemistry that you learned in organic molecules occur this the same way in bioorganic molecules. There's no magic and whoopie-doo or abracadabra. No, people like to say that, but it's not. In other words, the functional group chemistry going on in your body is the same as we've studied. Ester acid and water breaks down to give you carboxylic acids, fatty acids, and alcohols, glycerin. And I'm not ever going to ask on a test, but a biochemical substance is a chemical found in something alive like you. Now, let's talk about carbohydrates. I think I'll be subtle. Hint, know this. You should know the definition of what is a carbohydrate. And a carbohydrate is a polyhydroxyl aldehyde, a polyhydroxyl ketone, or compounds that yield such polyhydroxyl aldehydes or ketones upon hydrolysis, which means adding acid and water, or just water in some cases. Now, what's the word poly mean? That means many. What's hydroxyl? Did I say hydroxyl? I think I should have said hydroxyl. That's an OH group on a carbon. So carbohydrates are aldehydes, which have a lot of hydroxyl groups, alcohols in it, or ketones with a polyhydroxyl, a lot of alcohols in it, or compounds that when you react with water or acid and water make compounds that are polyhydroxyl aldehydes and ketones. Now, here are two very important carbohydrates. Normally, most of us think of carbohydrates as starches, which are carbohydrates, but glucose and fructose, these two simple sugars, are also carbohydrates. Now, one thing I'll teach you more about, this is called a Fisher projection. And I'll teach more about it, but every intersection of a line, there's a carbon here. Same thing here, 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 and here. Now, you do not have to, here's my gift to you on this Wednesday afternoon. You do not have to memorize the structure of fructose or glucose. It's good to be familiar with it, but I'll never ask on tests, what's the structure of glucose? What's the structure of fructose? Or what's the name of this compound? But you should be familiar with it. Now, if we look at glucose, my software and sugar chemists, carbohydrate chemists write aldehydes like this. If you go back and look at the chapter on aldehydes in that slide, this is how we normally do it, but sugar chemists write this like, whoop, I'm so used to not being a sugar chemist, which I'm not. This is the same as this. Therefore, this right here is an aldehyde. And notice a carbon with 1, 2, 3, 4, 5 hydroxyl groups. That's polyhydroxyaldehyde. And that's why it's a carbohydrate. That's glucose. And I'll remind you later on, this is the sugar, most abundant sugar in nature, and it's the sugar in our blood. Now, the other one is fructose. And fructose here, if you look at this right here, I have a carbonyl, carbons here, and carbons here. I call that R. I call this R prime. And what do we have here? A ketone. So this right here is a carbonyl of a ketone. Carbonyl, carbon, double bond to oxygen. And if you notice, right up here, I have a hydrox group on a carbon, another one, 2, 3, 4, 5. So that's polyhydroxyl ketone. So fructose is also a carbohydrate. Now, fructose, and I'll mention this again later on, is the sweetest of all. These are also called sugars. And fructose is about, I don't know how many 100 times sweeter than glucose or table sugar. And you'll find it for many years now, food manufacturers have been using fructose instead of table sugar, which I'll teach you is sucrose. Now, there's some definitions I want to run through because you might need them for other classes, but click the switch. Will this ever be on a test? For this part is in the off position. And there's something called a monosaccharide, which is a carbohydrate that contains a single polyhydroxyl aldehyde or ketone. Again, switches off here. And fructose and glucose are monosaccharides. Now, I hope I'm pronouncing this right because I am not a carbohydrate chemist. Unfortunately, Dr. White does love his carbs, spaghetti. The real bad ones are Lay's potato chips. The sour cream and onion are my downfall. But anyways, oligosaccharides are carbohydrates that have 2 to 10 monosaccharide units chemically bond together. Like if you had 10 glucose molecules bond together. Again, switches off for this. Now, there is one special oligosaccharide I'd like to talk about and you should know about. And that's called a disaccharide. Di, if you remember, like dimethyl means 2. And this is a carbohydrate that contains 2 monosaccharides that are covalently bonded to each other. And the most common one is sucrose, which is the common chemical name. You know that as the sugar or table sugar. And you should know sucrose is table sugar. And later this chapter, I'll teach you what two monosaccharides are bonded together to make table sugar, sucrose. I bet you never thought about it. Ooh, time for a Dr. White face-to-face moment. I bet you never thought about it. The white stuff you put in your tea, coffee, or on your cereal or whatever when you cook, that's a chemical. It's an organic chemical. It's a disaccharide. Two different monosaccharides bond together. Now, how it makes your tongue tell your brain, this is sweet, this is good, I have no idea. That's not my area of expertise. But as an organic chemist, I do know the chemical structure. Now, we have what's called polysaccharides. And poly means many. And a polysaccharide is a molecule, again, for this, the switch is off, made up of many monosaccharides bonded together. And we have also another name for that, and that is a starch. Starches are polysaccharides. Think of like a freight train with 100 boxcars. Well, starches are like that, except instead of boxcars, you have monosaccharides like glucose bonded together. All right, one of the things, and do I have models here? Sort of. I'll bring them more on. I'll talk about it in Monday's lecture. Remember, Monday, I'll post Monday's lecture on YouTube because I'm not going to be here. I'm going to be having this eye cataract surgery, and 2 weeks later, this eye. And because I've got, thank goodness, everything videotaped from previous semesters, I can just cut and paste and redo that sort of recycle stuff for you, but it'd be just as good if I were live. And if you want, you can always stop the video and roll back. Now, what I was about to talk about is molecules exist in 3 dimensions like our hands. And because of that, there are important ramifications. And the study of molecules in 3 dimensions has a name and is very important. And we're going to go through that, a little of it right now, because I see at 1:50, we'll take a 5-minute break. We'll do the lab, and then I'll send out the email for test number 3. Almost said this, not yet. Now, the switch is super on now. Let's talk about chirality. And if you're reading the book, I'd skip this chapter, but it's chapter 5, if you have the book. You should know. When we talk about chirality, there's a concept called handedness. And handedness is like your right and left hands. They're not the same. They're different. And I'll teach you that difference this part of the chapter. Now, one of the things you should know, what's the word chirality? Well, it comes from the Greek word chiral, for handedness. Chiral is Greek for handedness. Am I being subtle enough? Know this. And actually, about 2 years ago, it was amazing. I had 2 students who were fluent in the Greek language. I asked them, does chiral really mean handedness? And they said, yeah. So I have firsthand knowledge, and you can look on the internet. Well, at least firsthand knowledge. Yes, that's chiral for Greek. And by the way, it's not gyros, it's gyros, euros. They taught me that too. All right. Now, when we talk about chirality, something is very important you have to know about. And you probably haven't thought about it. And that's mirror images. I'm going to assume that all of you at one time in your life have stood in front of a mirror. And if we were at ECC right now, I'd say, well, if you have a chance, I know in the men's bathroom, well, actually washrooms, there are no baths in there, they have mirrors. I assume, and I've been told by students who are female students, that the female bathrooms have mirrors. And if you didn't have one, I tell people go stand in front. But when we talk about mirrors, there's two types of mirror images you should be familiar with. One is called superimposable, and that's when you have a mirror image when all points coincide with each other. You have an item and it's mirror image, you can push them together, lay one on top of each other, and all points coincide. Now, the other type is called non-superimposable. And non-superimposable mirror images are images where not all the points coincide, and you can't lay them together and superimpose them. So we have not superimposable and non-superimposable. Now, I think the second year I had this slide, or third year, some student raised his hand. By the way, Dr. White was always the first one down his spelling bee and said, you know, that's not superimposable. You have down there super impossible and non-super impossible. I said, that's why students are having so much trouble. They think it's impossible. I changed the spelling. So let's take a look at, just real quick, if I have a homework project for you. Go when you have a chance and you're at home or anywhere else where you can find a mirror. Most people have at least one mirror in their house. Put your hand in front of one of your hands in front of your mirror. Pretend I don't have my ring on, and look at the image in the mirror. You'll see this. If this is the hand, this is your mirror image. And if you notice, your hands are mirror image, and they're not superimposable on each other. My middle finger I can have lined up, but none of the other fingers line up. If I line up my thumbs, nothing else lines up. So your hands are non-superimposable mirror images. Take your hand, hold it up to the mirror, and you'll see this in the mirror, like this. Oh, by the way, I have to do this. I apologize immensely, but everybody know what this is? A spider doing push-ups on a mirror. I couldn't resist. I apologize. So you have superimposable mirror images and non-superimposable mirror images. And why do I have to talk about that? Because in chemistry, we have what's known as chirality. And chirality, you have two types of objects, chiral objects and achiral. And chiral object is an object that's not identical to its mirror image. A chiral object has a non-superimposable mirror image. Your hands are chiral objects, or chiral. An achiral object, A means without. A is a prefix meaning without. Achiral means without chirality. A achiral object is an object that's identical to its mirror image. In other words, it has a superimposable mirror image. So you have chiral, non-superimposable mirror image, achiral, superimposable mirror image. Your hands are chiral objects. So are your feet. And with that wonderful thought, I'm going to say it's time for a 5-minute break. Let's come back at 1:56 and we'll do lab on polymers. I'll see you in 5. Take a 5-minute break and we'll continue. Sorry about running a minute or two late. Let's get going. Let me also close something. All right, let's go through today's lab. Now, earlier I was sort of sad. Why? Because it would be fun if you were with me face to face at ECC to do this lab. And then afterward, I thought, well, when we do labs, at least organic labs where we have chemicals all together, where you get it, it's hard to keep social distancing. It would be very hard. And because I can, I've been able to do all the labs on Zoom with you. So even though it'd be fun to do this, I think for all of us to stay safe under the pandemic is a good thing. All right, let's talk about today's lab. Today's lab deals with polymers. And polymers, as you know, are repeating units connected together like a boxcars of a train. And we're going to talk about some fun polymers. And remember, they're very large molecules, polymers. They're very important in our daily life. And the word polymer comes from the word poly, which means many, and mer, single unit. And they're very large polymers that are repeating units. Now, the first one I'd like to talk about is polyurethane polymers, which I know a little about. Like I have, I think, 5 US patents in polyurethanes. And what is a polyurethane? Well, first of all, what's the urethane functional group? I didn't teach this in the lecture part, but if you take, this is called an isocyanate, and this is our group on a nitrogen, which is double bond to carbon, which is double bond to oxygen. Well, I didn't ask, but thumbs up, people. Do you all see polyurethanes on the screen? Thank you. All right, and you react that with an alcohol. This attacks the carbonyl carbon. Yes, that's the carbonyl carbon, carbon double bond to oxygen. A lot of functional groups have it, and it forms this new functional group, which has the name urethane. Now, how those two got those names, I have no idea. And I'm just thinking about it. How did alcohol get a name? Why didn't they just call that a foot? Who knows, but that's what happened. And this is a urethane. Now, if you have a polymeric isocyanate, more than one, and a polyol, more than one hydroxyl group in a molecule, you'll get a polyurethane. And like I said, this is a urethane reaction, making a polymer, polyurethane, when you use like a diisocyanate with a polyol. Now, this is an exothermic reaction, gives off a lot of heat. And to make a urethane foam, which is probably one of the main uses of polyurethanes, you include what's called a low boiling liquid, which is a blowing agent. I had a brain freeze there for a second. And because of the exothermic reaction, the liquid that has in there your blowing agent expands, becomes a gas. And that's trapped in the urethane and it makes a foam. Now, how many of you have ever purchased or had bread from a really good bakery or made your own? When you slice the bread, if you look at the surface, you'll see little cavities, which are the bubbles you cut up when you cut the bread. Bread uses yeast, which makes carbon dioxide, and that expends the dough to make bread. Bread is really a foam. I bet you never thought that. But anyways, urethanes do that. Now, one of the main uses of urethanes is in insulation or urethane foam. And to make it very simple for people at a house or in a factory to make urethane foams, manufacturers came up with a concept called A and B sides. And let's talk about that. And you'll need this to know this for the questions on the lab. Now, the A side is this the isocyanate? It's really a polymeric isocyanate. Now, the B side contains the polyol, poly, many, OL, alcohol. And it also has the blowing agent, and to make this go faster, they add a catalyst, which is in the B side. And since you now know organic chemistry, the widely used catalyst is a tertiary amine. And I showed you that dimethyl cyclohexylamine. And finally, to get better bubbles, more consistent or better distributed bubbles, they also add a silicone. It's called blowing agent, or just a silicone, not blowing agent. My mind's on next Monday. Sorry about that. A silicone surfactant. And what you do is you take equal parts for most formulations, A side, and mixed with B side to make a urethane foam or polyurethane foam. And let me get something. Down here, I have hidden where it says C. Let's take a look at this. Everybody see the YouTube on here? No, I don't want TV.
Today we're going to talk about molding foam. Specifically today we have a 3 pound per cubic foot molding foam that we want to discuss some of its attributes. This material starts its life off as thin liquids. It's going to be mixed at a 1-to-1 volume measurement, and then it's going to expand. It's going to expand to form a very lightweight foam. And as we said, in this case, it's a 3 pound per cubic foot density foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing, closed cell foam that can be easily sanded or carved to dimensional shape. It can be cast as backups or as freestanding forms. It can be painted with automotive paint. A flat spatula, not a round. We're going to measure out, actually be mixed and used. Also, it's good down to depths of be mixed and used. We first conditioned our liquids to 72 degrees Fahrenheit. Best temperature to be at. Hotter means faster reaction. Colder means a slower reaction is going to create higher density foam than desired. We're going to measure out in equal portions in liquid. In this case, we've had some pre-marked beakers. We measure out part B, and now we're going to measure out part A.
Notice that's polymetric and very brown.
And then we're going to take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the A and the B.
See the color
So they
change?
get fully reactive. Doesn't take much. When the material starts to react,
All right, I'm gonna back this up. Notice the color change of the material in the cup. It looks like cream and coffee, doesn't it? You think about it. Here, the material in this cup is very dark, like black coffee. By the way, Dr. White doesn't like coffee. I'm a tea drinker, but still looks like coffee.
of the container to incorporate all the A and the B.
See how
So they
quick-
get fully reactive.
See how quickly it changed color? That's called the cream time, because someone said, oh, looks like the color changed when you put cream into coffee. And the cream time, you should know, and I'll write it down the whiteboard in a little while, is when the urethane reaction starts. And you can adjust the cream time by adding more or less catalyst. More catalyst, faster cream time, faster reaction. I mean, a smaller cream time, I should say, it happens quicker. Slower reaction, longer cream time.
The heat on its
And
own, again, 72 degrees is the perfect temperature to start mixing that. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own and it could warp your mold. So now it's starting to come up. And actually, to demonstrate this, we're just going to let it come up to kind of show you what we call free rise in this. So it comes out,
you see the foam
it's going to
forming
expand.
in the
And
lab?
within about 2 or 3 minutes, it's going to get to be full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now, because it loves to stick to human hands. That's about it. And you can see I only had about 500 milliliters of liquid, but you can get a sense of how much volume with this. Now, foam is sold in different densities, from very, very lightweight packaging foam, which is about 3/4 of a pound per cubic foot density, all the way up to heavy furniture foams, which can be as high as 15 to 20 pounds per cubic foot. And every time they go up in density, the carvability and the machinability goes up to it as well. You can see this is already forming a nice solid. And within a few more minutes, I'll be able to pick this up and actually carve it for you. Well, it's only been about 5 minutes since we initially mixed our foam. And you can see it's pretty well set. It doesn't stick to polyethylene or propylene plastics, so common garbage bags work quite well as a barrier. As you can see, it's durable and it's fairly lightweight. And as we mentioned earlier, it's easy to carve.
Now, one of the things, you can adjust the blowing agent to adjust what the density is. Now, catalyst, depending on how much catalyst, how quickly you get a cream time, one of the badges of honor for someone who works on urethanes is to make the following. And this is my badge of honor. This is a urethane foam right here. And you have to practice. Took me 5 tries, which is pretty good. I've heard people spend a long time never doing it. And you, in this cup, you mix the part A and B, and you just, I don't buy it. When I did this, I did my own formulation, and you put enough catalyst in there so by the time you poured it and it hit the ground, it solidified, and that's my badge of honor. I hate to say this, but I made this in about 1984, and I still have it. It's one of my prized things. You can see how the urethane solidified as it was being poured out. But normally when you make a foam, if you're putting it in a mold, you want it that quick. Now, you can also have it very quick, so when it mixes together and you force it out with a spray gun, it immediately starts rising. And if you look on YouTube or other places, for insulating certain homes, instead of buying board stock of urethane foam, you can buy or you have it sprayed in. And that's usually in your attics, the inner roof joists and all that and sides, they'll use the spray foam. Now, one of the amazing uses of urethane foam, and this is called the solid urethane foam, because when it hardens, whether it's the lighter density, can you hear that? It's solid. And in the class, you'd make a solid urethane foam. Go look at your refrigerator. If you have a newer refrigerator made after, I don't know, 1970s, thereabouts, you'll see the walls are real thin. If you go back and look at pictures of refrigerators made in the 1940s and 50s, they're real thick. Why? Because in the past, they used glass wool to insulate the inner cold box from the outer walls. Now they use urethane foam. So urethane foam is an excellent insulator when it's a solid. Like my desktop is not urethane foam, but it's a solid. There's another type of urethane foam which has what's known as open cells, and it's flexible. And all the cushions in your furniture, your car, most of your pillows are flexible urethane foam. Now, there are a couple important things you should know. And when you're working with urethane foams, the cream time is an important measurement. That's from the time you mix it, the time it takes when the reaction starts. Now, there's another important thing called the tack-free time. And if you notice in that video, before it hardened, the gentleman doing that, touched the top to see if it was still sticky. And tack-free time is when sticky or tacky. And you can take a tongue depressor, which we use in the lab, and touch the top, and it takes a couple of minutes in the kind of foam we do. Now, the other thing is there an exotherm? Exo giving off therm energy, heat. And you would feel the outside of the cup be mixed in. And if we were face to face, you do it. And guess what? I'll give it away. It would get hot. And that's what makes the blowing agent expand to make the foam. And notice here, I give you the cream time, tack-free time. Was there an exotherm? Did it heat up? Yes. What did it look like? I had people do that just so they get to look at things. And it was solid, like I showed you, light brown. Now, the next reaction I want to talk about is making polyamides, polymers. And you know them mainly as nylon. And normally, to make an amide, you take a carboxylic acid plus an amine. But a derivative of a carboxylic acid that reacts quicker is an acid chloride. Now, what I don't have here is, because This gives off HCl, and normally you have a base in there to neutralize this. And this reacts to give a polyamide, and you would be making nylon. By the way, up here, I didn't mention it. Here's the procedure. You can read it on your own if we were, similar to what you just saw in the video. Now, in terms of polyamide, nylon, you would mix together in 2 beakers, an A and B. In the A beaker, you'd have a solvent, and you'd weigh out this acid chloride called sebacyl chloride. And in beaker B, you'd weigh out a certain amount of water, some diamine, hexane 1,6-diamine, that's already a solution, stir it, and then you'd add some base in there. That's the base you need to neutralize any acid, and you'd mix it. And what you do is, here's your A, and very carefully you tip this so it really looks like this, and it's got the chemical in there. And here is your B beaker, and very carefully down the side, you pour that, and in the A beaker, after you pour it in, you'll see, by the way, you're all permitted to laugh really good at my artwork. And what you do is take a little wire hook, and this interface right here, the two are reacting together and form a nylon. And you pull this up and you wrap it around a beaker and you start making nylon. And the students love, after this
So I've got my
commercial,
essay written, and I've been working on it. Familiar mushroom cloud snake skyward, hurling the atoms.
This is the aqueous solution. I'm going to pour this in here. And that aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine that's dissolved in hexane. And hexane
this would be
is
your
less
B
dense than
beaker.
water.
He has
So
an
this solution is going to
Erlenmeyer.
float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this reaction is going to take place. How many fingers do I have? Anyway, there we go.
Doesn't know how to put on gloves.
These were gloves for another species. Here they are.
And during
Okay.
the lab, you would
So
be
I'm
wearing
very
glasses.
carefully going to pour this down.
See
the
how he's
side,
doing
and
this?
then where the interface is, we'll have contact between the diacid and the diamino hexane.
And that smoke is some HCl already being
Hexane
formed
layers
that was
forming on the top there.
neutralized.
But of course, where they come together is where the polymer can be made, where the condensation reaction is happening.
See the
So
interface
then I'm gonna
between
reach
there?
in here,
Watch.
and where the interface is, I'm going to pull out some nylon.
We use that white stuff as nylon.
See how much nylon we can pull
And we
out
wrap it around a beaker instead of what
There's
he's
a meter.
doing.
or so.
And you keep on doing this for
Two.
about 4 or 5 minutes. That's a lot of fun.
There
Again,
are
we don't do what
records
he's
set to
doing.
this.
You just
And,
wrap it
so-
around a beaker.
I think it's actually in the Guinness Book of Records.
And like I
Sure, we're gonna
said,
beat
you
that
can
record
keep on
today.
going. It's like the Energizer Bunny.
Yeah, yeah.
It doesn't want to stop.
Right.
And that white material he's making is all
Now, you
one
can see that you can get a
long
lot of
polymer.
material out of a very small quantity. I only dissolved a few grams of the acid and the
And this one, you'd make the polymer. And later on, you'll see there's some questions. There's no data other than when we're face to face. I say, when you're making the polymer, call me over because I'd like to see it too. It's really neat. Now, the last one is the reaction of alcohols with boric acid. And being lazy, I forgot to put the reaction. Boric acid, actually, we use sodium borate, but this will and this is a reaction I don't teach in the lecture. And this is called the borate ester. And if you have a polyol instead of a single alcohol, monohydroxy alcohol, you'll make a polymer. And here, what you'll do is in a beaker, you'll put in 50 milliliters of, or actually about 2 milliliters of the alcohol being tested, and then 5 milliliters of water and mix the solution. After that, you add some boric acid solution. It's really 20 multein borax. And the two you're going to be using is isopropyl alcohol, which you know what the structure is, and then polyvinyl alcohol, actually Elmer's glue. Now, PVA has this structure. Where N is on the order of 1 million. Well, that's a lot of alcohols. And what you do is you make this complex polymer, where here, isopropanol, otherwise known as 2-propanol, I'll help you out, is not a polyol. And if you think about it here, when you have the alcohol being PVA, polyvinyl alcohol, you're going to have a lot of these borates connected together and you make a repeating unit. And here I ask you mix together and see what you observe. And what you observe with the 2-propanol isopropyl alcohol or isopropanol is a clear liquid. When you mix the borax with the PVA, Elmer's glue, you get, I like my description, gooey, slimy, white solid. By the way, this is how they make monster slime for the movies like Star Wars. Remember the first Star Wars where that monster, no, it was the third one with of the original series, when the monster had the goop coming out of his mouth? Well, that's how they make it. And let's take a look. And I have the links in the lab, so feel free.
So let's say you have to read an incredibly
Time out for commercial. Dr. White didn't spend money to get commercial-free YouTube. Nope, I picked the wrong up. Sorry about that. That's a weird video. I forgot. I don't know why they have a mushroom cloud there. All right, this should be the right one.
today I'm
All
done
right.
today with a purple color. For some reason, it's looking.
And here's
I
the
chose
Elmer's
purple
glue.
because we currently have a million
put-
different slimes at
they
home. So
put
we
in
have
a
a butter
food
slime that's yellow. We have 2 fluffy slimes that are pink.
She puts in a food coloring. I don't, because it stains your hands if you're not careful, even with wearing gloves. So we stay away from that in the lab at ECC. But if you're at home, you can do that. All that is Elmer's glue and water. And now they're going to add now she adds it in a small amount. We just dump it together and have some fun. And as you'll see, and you can play this video for yourself, see how it's starting to get thick in there when you add more of the borax, the boric acid. And adding more, I'm jumping through. See how it's starting to get gooey and thick. Dr. White's having a good time watching this. And then more. And now it's getting like this. To the point, you can take it out and play with it, and students do. And that's the polymer made with polyvinyl alcohol, Elmer's glue, and borax. If you want to do this on your own at home, all you have to do is get some Elmer's glue and some 20 mule team borax. Mix the borax and water, mix it with the Elmer's glue, just like she did, and you'll get the same results. And with that, I'm done for today. Let me remind you, in a couple of minutes, about 5 minutes or so, I will be emailing out the password for test number 3. You have until 11 a.m. tomorrow to finish. Should take you about 40, 45 minutes. If you need extra time, take it. I won't tell. And just don't cheat. Don't go on the internet. Don't look at your notes. I'll know. And I have secret things in the test to tell me if students do that, and it works. But anyways, take the test. Remember, if you have any questions, come to my office hour. Now, tonight I have some more errands to run. So after my office hour, I probably won't be back until later. So if you have email questions, I'll answer it either late tonight or tomorrow morning. And I won't be seeing you until a week from tonight, because on Monday, I'll be having my first cataract surgery. And then on Sunday, I'll send out an email that the Monday lecture is now available on YouTube. So don't show up next Monday, and I'll see you a week from today. Gang gesund. Goodbye. Have a nice rest of the week and weekend. I'll see you next Wednesday. Bye now.
Thank you.
You're welcome.
Thank
you. You're welcome, Joe. And if you have any questions, I'll stick around. If not, gang gesund. Goodbye.